Okay, well now I'd like to talk about an interesting device called the single electron transistor, another application of quantum dots. Only this time, the quantum dots won't be semiconducting, but they'll be metal or conducting, okay? Here, let's take a look at this interesting application. Okay, so it's in a single electron transistor, we have a source and a drain and a gate, 3 contacts, but the channel of the transistor is a quantum dot. And the operation of this transistor depends on it being so small that adding one more electron to the channel appreciably changes its energy. In addition, the connections between the source and the channel or quantum dot and the drain are what are called tunnel junctions. That is, they're not direct connections. Instead, they're barriers, and electrons have to tunnel across these barriers to get into or out of the quantum dot. Here, let's take a closer look. And as we do this, we're going to start by first considering the charging energy of a quantum dot. And then we'll talk about a simplified version of this, which doesn't have a gate electrode, okay? But will exhibit an interesting phenomenon called Coulomb blockade. Finally, we'll talk about single electron transistors, okay? Here, hang on for one moment. Okay, let's consider the charging energy of a quantum dot, a metallic quantum dot. So imagine I have one of these, which we'll take for the moment to be a sphere. And suppose this sphere has some radius r, and it's embedded in some dielectric with dielectric constant E sub r. Finally, let's imagine this carries a charge, Q, which is just N times E. It carries a charge because it has an excess of electrons, an excess of N electrons, okay? Let's calculate the energy required to bring one more electron to the surface of this quantum dot. So the energy required to bring in one more electron, delta U, is just equal to the charge that we want to add times the potential at the surface of the sphere, electrostatic potential. So we just have to remember the electrostatic potential of a charged sphere, okay? And of course, that's no problem. It's just the following. It's equal to the charge on the sphere divided by 4 pi epsilon naught, 1 over r, where r is the distance from the origin. And so it's, since Q is NE, this will end up being N times E squared divided by 4 pi epsilon naught epsilon r times r. I'm sorry, I left off the epsilon r in the previous expression. Okay, and that's our result. Perfect. That wasn't so hard. Now, let's suppose we pick some parameters. Let's suppose that n is equal to 10. We have an excess of 10 electrons on the sphere. And let's suppose that r is equal to 10 nanometers. Let's suppose that the dielectric ratio is 5. Let's figure out what delta U is in that case. Okay? I mean, this is just a calculator problem, so you can go ahead and figure it out. But if you don't mind, I think I'll just write down the answer. The answer is 0.29 electron volts. And that's kind of interesting, isn't it? I mean, it's an appreciable energy. It takes an appreciable energy to bring another electron to this quantum dot, basically because it's so small, because r is such a small number. What's interesting about this number is, well, it's about 10 times Boltzmann's constant times T at room temperature. So that means that the state with 10 electrons on the quantum dot and the state with 11 electrons on the quantum dot are distinct enough that that they're distinct from each other even at room temperature. Electrons aren't going to just randomly fluctuate back and forth on and off of this dot because it requires too much energy. Okay? Okay. Oh, say, here's another look at the same problem. So another way we could think of this is we could say that the sphere has an electrostatic energy, U, which is given by the charge on the sphere and the capacitance. It's just 1/2 Q squared over C, as we remember from physics 2, okay? Here, Q, once again, will be N times E. And then we'll look at the capacitance in a moment. In any event, then the change in the energy when we bring in one more electron is nothing more than the derivative of U with respect to N times the change in N, which would just be 1 in this case. So this is derivative with respect to N of Q squared, so N squared times E squared over C, which, oh, I'm sorry, and I forgot the factor of Q, there we are, which of course is super straightforward, N E squared over C. Now, if our quantum dot is a sphere, then for an isolated sphere, we know what the capacitance is. Let's call this the capacitance, the self-capacitance, okay? And then presumably there'll be capacitance due to the presence of other conductors around it, which we'll very imaginatively call C other. Now we can see where our previous result came from. The self-capacitance of a sphere is just 4 pi epsilon naught epsilon r times r. And so if we ignore the capacitance of everything else, then we find that delta U is exactly what we found before, okay? N E squared over 4 pi epsilon naught epsilon r times r. But now we know how to include the capacitance from other conductors that might be nearby. So if the dot is very small, then we might expect that the self-capacitance might dominate, or at least the capacitance due to other conductors nearby, it might be of the same order. And so in that case, we expect that we can get an appreciable charging energy when we add just one more electron. Okay, either way, we get the following picture. There we are. So this quantum dot has energy levels, which we can draw in. Okay, where the energy depends on how many of the energy levels are occupied. According to the formula that we wrote down a moment ago, N squared E squared over 2C, okay? And in any event, here we are. And then delta U is just the energy difference between the highest occupied energy level and the next one. But there's something interesting about these energy levels. In this case, these have nothing to do with quantum mechanics. I mean, except for the fact that the electron charge is quantized. Okay, there's no H bar in our formula for U. In addition, each state just holds one electron because the only thing that matters is the charge of the electron. Every time we add another charge, the energy of the system goes up to the next level. So anyway, that's an interesting picture. And it turns out that there's a range of sizes over which this electrostatic energy levels are more important than the quantum energy levels that we would see if the dot were even smaller. Okay, so here's our picture now. Imagine that we have our source and our drain, or our left and right conductors, and then in between we have our quantum dot. The source and the drain don't touch the quantum dot. Instead, these are tunneling junctions. Electrons can tunnel through the junction, but that's the only way to get there. In that case, our structure looks like this. And for a moment, I just want you to think, oh, this looks like a resonant tunneling diode. Only now, the states inside, the confined states inside of the diode aren't quantum states. They're these electrostatic states of our metallic quantum dot. But otherwise, it's very similar. And the same principles control the flow of electrons here. If we're in a situation where the energy of the particles on the source side do not line up with one of these energy levels, then transport is difficult because we would have to tunnel into a state of higher energy in order for the electron to enter the dot. There's an energy barrier, or what's called a Coulomb blockade, that prevents the flow of current. However, if we change the voltage between the source and the drain, then we'll essentially lift up the energy of this state relative to the states of the quantum dot or to the right side. And eventually these will align. And when they align, then the electron can rapidly tunnel into the dot. And then it can also tunnel out of the dot because this process obeys energy conservation. I mean, the dot can tunnel out and then give up its excess energy as heat. So here current can flow, but here it cannot. Because of this, we expect that a current voltage characteristic of a system like this would exhibit the following. At low voltages, no current can flow, okay? We're in what's called the Coulomb blockade. But once we reach this condition, we'll switch on current through this channel, okay? And we'll have some finite current can flow. If we keep turning up the voltage, we'll actually align the source, the energy of the electrons in the source, with the next confined state. And then the current will increase again. Essentially, now we have two channels that conduct electricity, one through the state here and one through the next highest state. And if we increase the voltage still further, we'll get another jump and another jump. This pattern is called a Coulomb staircase. Lovely terms, right? So for very small quantum dots or metal islands between source and drain conductors, we expect to see this interesting kind of current voltage relationship, including this switch between off and on. Here, I want to show you a device now. There we are. So this is a system like this that was described in a paper from a few years ago. Just to describe it, in this system, we have a source and a drain that are separated by an insulating barrier. And then they decorated these, they made a lot of these, and they decorated them with gold nanoparticles. And some of the gold nanoparticles ended up sticking to the dielectric in between the source and the drain. And now these are the quantum, the metal islands between source and the drain that will act as, that will allow these funny effects, Coulomb blockade and Coulomb staircase. So they made it this way because they want to make the dot very, very small to try to get room temperature operation for these devices, to have energies that are large enough to be distinguishable at room temperature. And here's what their data looks like. So this, again, is at room temperature, and you can see clear steps in the current voltage relationship due to this Coulomb blockade effect. That's pretty cool. Okay, now this effect, the finite charging energy of a small metal island, can be made the basis of a device, a type of transistor called a single electron transistor. Let's take a look at that. A single electron transistor looks a lot like the structure we just talked about. It just has one more connection. So we have our quantum dot. We have a tunnel junction connecting the quantum dot to the source and to the drain. And then we have one more junction, now just a capacitive, not a tunnel junction, just a capacitor type. So just a capacitive junction to the gate. So basically, this is the same system we had before, but now we have another way of changing the energy levels in the quantum dot. Not only can we change them by changing the amount of charge on the dot by tunneling through these tunnel junctions, we can also pull them up or push them down by adjusting the voltage on the gate, okay? So we can change that. We can also move the energy levels up and down electrostatically. So the idea is that in one case, the energy levels might align like this, and we have a Coulomb blockade and no current flow. But if we adjust the voltage on the gate, we can pull the energy levels up or push them down until we get alignment. And now electrons can tunnel across onto the island and then tunnel off. Yeah. In the first case, no current flow is possible because the electron would have to jump up in energy in order to enter the island, because all the lower energy states here are all full. But in the second case, the electron can jump onto this island because the state is unoccupied and aligned in energy with the source. And then it can tunnel off as well, okay? Notice something interesting though. We get this flow of current, but it has to be one electron at a time. Once an electron tunnels on, no more electrons can tunnel on until this one tunnels off. So in that sense, also, this is a single electron transistor. Here, let me show you some results for a single electron transistor. The first one is a single electron transistor at low temperature, at 4 Kelvin. This is made out of graphene, our favorite nanomaterial. And here they used, I think, an electron beam to cut a sheet of graphene into this shape. Okay, it's like a stencil almost, or a cookie cutter. And you have a source, the drain, and then the quantum dot is this island in between. And then you have a gate contact over here. And what they're showing is changes in the conductance of the transistor, so the conductance from source to drain, as a function of the gate voltage, okay? And what you find is that at certain values of the gate voltage, the conductivity is high, like this. Whereas at other voltages, it's low, like this, because the levels aren't aligned. So this looks really great. I mean, this works really well. The only problem is that it's at 4 Kelvin, which is a little inconvenient for most applications. But other than that, it's fabulous, right? Now, it would be nice to be able to make single electron transistors that work just as well at room temperature, but this is much harder. In order to work at room temperature, we've already seen that the dots have to be very small, with radius of 5 or 10 nanometers, or smaller if possible, so that the energy difference between the different charging states will be large compared to KT. Here's one example of a single electron transistor built on silicon. And the details are shown here. And you can see how this works. If we look at conductance as a function of gate voltage, in this case, the quantum dot is very small, I think 5 nanometers. And you can see that the, actually, I don't know how small it is. I'm sorry, I just forget that. But you can see at low temperature, which here is 42 Kelvin, you can see these clear peaks in the conductance. So this would work really well. But as the temperature is raised, everything kind of smears out until at room temperature, while you can still see the features, they're quite weak, okay? So single electron transistors work really well at low temperature. And it's possible to make single electron transistors that work at room temperature, but not very well. Moreover, they're very sensitive to the exact parameters of the device, the size of the quantum dot, the tunneling, the properties of the tunneling junctions. So that makes these difficult to be find wide application. There are some scientific instruments where it's important to have the highest possible accuracy in an electrometer or in a current sensor. And there, single electron transistors are used even now. But it has to be worthwhile enough that you're willing to operate this part of your apparatus at, liquid helium temperature or something like that. Okay, well, that's an interesting application of quantum dots. I'm going to stop, come back to the main room here, which I wanted to show you. It's interesting because, well, these are neat devices, but also they're devices that work on quantum principles. Tunneling and quantization of charge are important. They're what allow a single electron transistor to work. They're not problems for these devices. They're the principle of operation, okay? And I wanted to show you that semiconductor quantum dots already have wide application as fluorescence emitters. But here, I think I'll wrap this up. And with that, we'll wrap up our discussion of nanostructures. All right.